Hello, everyone. Good morning. So today I'm going to present my research topic here in the FIOP, and is the main topic actually is concerned about the assessment and retrofit on non-seismically conforming existing reinforcing concrete structures. And then we're going to validate and check the Eurocode 8 Part 3 recommendations. Okay. When I'm talking about non-seismically conforming structures, we're pretty much talking about old structures. My name is Yuri, and this is a part of the project RC Seismic Reinforced Concrete. Okay, I hope you can enjoy. Today we're going to be speaking about a brief introduction, a state of art that was my primarily focused, and I hope I can go with you through very interesting topics that we have researched so far. I'm not here to talk about the main results that we found, but I just want to teach you a few things about old structures towards seismic performance. I'll go through very short things about methodology and experimental numerical campaigns, which are still under development. If you have any questions, you can feel free to ask me after this meeting, okay? So a brief introduction is, what is a non-seismically conforming reinforced concrete structure? Pretty much it is an old building, okay? And what is this old building? Why we have concern about this old building? Well, in the seismic scenario, it's a building that was not designed to resist lateral load. Okay, so it's pretty much a building that was created prior to the 70s and 80s seismic standards. This includes the United States, Europe, and Japan. Okay, primarily these buildings are designed for only gravity loads. They have lack of any capacity design principles, such as like strong beam and weak column. We can identify low ratios of longitudinal and transversal reinforcement steel, so not enough stirrups, both in beams and in columns, nor in joint panels. Okay. We also have inefficient anchorage. For example, we would have like 90 degrees hooks instead of 135 or 180-degree hooks. Short embedding lengths in support regions too. Presence of lap slices. This is a very concerning thing too, but is a reality because we can build a reinforced concrete structure with longitudinal bars everywhere. Also, we would have low quality materials. So back in the day, 10 megapascal concrete was a very strong concrete, and 30, 40 years later, it's a very low quality concrete. Also, we have different types of aggregates that have been used, and also high water cement ratios. And something that I want to focus is the smooth bores. Okay, this is a characteristic prior to buildings built before the 60s. Okay, here are some examples of wrong details that we actually see when we're talking about seismic performance. So lat splices, lack of shear reinforcements on the panel zones, longitudinal rebars that change directions, not enough stirrups. We'll have stirrups that might be opened. This is actually really concerning in seismic prone areas, and very beam columns that have not enough strength towards flexion. Other examples here in columns, lap splices, and details of 90-degree hooks at stirrups. This cannot provide sufficient confinement, and this is an main example of smooth bars with lap splices. Here are some examples that we have seen in regions that have been just hit by earthquakes. So this is during the reconnaissance survey in Turkey. Buildings that are not reinforced concrete well prepared. So for example, lack of continuity. Here we have not enough reinforcements in the transverse directions. We have buckling of longitudinal reinforcements. Also use of smooth bars or plain bars. Other examples here, use of plain bars, also not enough stirrups in the region of connections, also in columns. We have inadequate lateral reinforcements, poor arrangement and not good and confinement of longitudinal rebars. This is a main problem that we are talking about. This is towards the beam column connections, which can create a brittle failure and overall building collapse, and also a joint anchored failure. Okay, you can see here that joints were pretty much damaged and the other members were not as much. Other examples of joint failures, and you can see that actually these members, adjacent members, are not too much damaged. So specific about plain bars, and well, pretty much reinforced concrete structures, we assume that reinforcing concrete has a perfect bond between concrete and steel. Okay, is it though? So for example, we have a pull-out test here in which we can check how much is the bond strength between reinforcing steel and the surface concrete. And with that, we can actually pretty much define the bond stress. Okay, so talking about bond strength, we have pretty much three mechanisms of resistance. We have chemical adhesion, we have also friction between materials, and also we have, in the case of rivet deformed bars, we have the indentations, what we call lugs. And a lot of the bond strength comes from the reaction of these lugs. Okay, in plain bars, on the other hand, we don't have that. We have a smooth surface. And this is a very concerning problem because the only two resistant forces are these two previous. And when we have pretty much slip, these forces, they drop significantly. Okay, so this is a very major problem. And still talking about deformed bars, something that is really important is when we have the lug action, we have a creation and a spread of a very tiny cracks throughout a very large length. So one good thing about deformed bars is because this creates a cracking pattern that is easy to identify, and it actually gives a lot of strength because a lot of the surface of concrete will be working together. Okay, and plain bars, on the other hand, especially because due to Poisson effect, which the bar shortens when we are tensioning, we don't see that development of full cracks, which means bars are not fully integrated with the concrete, and thus this violates the perfect bond assumption. So this is an example of slip. This is a bar, a bended hook in the pull-up test, and this is what we call a slip. So the bar is not actually attached, even though there is a hook. When the hook's been pulled, the bar has been pulled together, so it loses this adhesion part because of the slip. And this is actually a graph that shows the strength, the bond strength by bar slip. Okay, strength and stress, we will be used in the same place. So we have here a pulled out test, and when we start pulling out that bar, we have this slip. Okay, and then we start actually measuring that slip. In plain bars, as you can see, after you have the first crack, okay, you lose a lot of strength because of the slip action. So the bond is pretty much lost, and what we get here is a residual stress that goes all the way. Okay. On the other hand, if you have deformed bars, you can have much wider stress, okay, and long bar slip. In other words, deformed bars, they have actually more ductile and more strength, okay. And when you take out the confinement part of deformed bars, you actually lose that straight away, that bond. On the other hand, when you increase confinement, you actually increase the strength. So confinement is a very important and a particular part of this bond strength. And here's the other thing that I was wanting to show you. So when we have critical sections, when we made these critical sections with deformed bars, that very short length pattern with several cracks, it's easy to identify. Whereas when you have specimens made of plain bars, this crack pattern becomes a much wider crack. So cracks are like thicker, and they are very much spaced around the zone that has many stress, like much stress. Okay, so this is a characteristic about this. And speaking about critical sections, let's just take like a regular 2D frame, as you can see, which is pretty much loaded in vertical loads. Okay, and also we put here horizontal forces that would simulate an earthquake, for example. When I check the bending moment made by the vertical loads, we see that pretty much the maximum loads or maximum internal stresses are concentrated in the beam column connections and the middle span of beams. Okay, and on external columns, you might see a shift in that, right? Also, when you see only the horizontal loads of earthquake, you see that the stress concentration is actually on the internal columns and external columns on the first floor primarily. And when you have a combination of both, you see that actually in reinforced concrete frames, the most part that is subjected to internal stress is the first floor, beam column joints, columns, and at the end of beams and the floors. So this is something that is really important. Why do we actually need to have attention to columns and beam column joints? Well, first of all, columns are the main parts of the frame that resist lateral load. Okay, so if a column fails before a beam fails, we actually expect a sudden mechanism. Okay, the failure is expected to be sudden. Also, in beam column joints, two major problems related to it is that these elements, as you can see here, they transfer the internal stresses from beams to columns. So if these units can no longer transfer these loads, that means the other adjacent members cannot reach their full plastic mechanisms. Okay. In other words, even though if you designed a building with capacitor design principles, if you don't check the strength of beam column joints, that capacitive design cannot be promoted. Okay. So how can we test actually columns and beam column joints to see cyclic capacity? So we have pretty much a few examples that we conduct in experimental tests. The first one is when we use bidimensional test setup. Here's actually supposed to be bidirectional. Okay. And what we do is that we take a sample size of the structure. Okay, actually it's like this is pretty much a beam column. And we do what we call a quasi-static displacement control test. We get the column and we start like uploading load at the top of the column, and then we come back. We do that as a cyclic test. Usually we have this load protocol, which is similar to Euro code and American standard. And then we can do that until we detect failure. Okay. Other examples that we can do is that we can do this in a three-dimensional way. So this is more difficult because, well, you have to have much more investment and you have to have distance setup. And this is actually very difficult to build. Usually we do a 2/3 scale or 1/3 scale. All right, so we can build up these models and we can test. And they are actually made of a small part of the building. And then we can, after running this test, we can do like numerical validations. Another example that we can do to see seismic performance is literally using shaking tables. So in order to do that, you have to build up a sample size scale frame in your lab over a shaking table, and then you can come up with specific ground motions from real earthquakes and just simulate. Okay, this is much more expensive, but is more related to reality. Okay, and once we can run these tests, how can we measure cyclic capacity? Well, we can usually come up with this, which is what we call capacity curves. So we can check hysteretic behavior. So we have here what we call the displacement by force, and we measure the displacement in terms of percentage, what we call drift. Okay, and so we can do like a cycling, and then we can enhance the cycling and see all the way until the failure is reached. And then we can see a pattern, we can see a pitching effect, we can measure maximum strengths, we can measure joint crack, and etc. Okay. With that, we can determine the yielding and ultimate drift. We can define force displacement envelope curves. We can check the strains and the joint panel deformations. We can assess energy deformation capacity and stiffness aggregation. We can also check damage and crack evolution. And finally, we can calculate ductility levels and equivalent damping. Okay. An important measure that we do during this test is how we can define failure. So we usually define failure by a percentage of the maximum strength that specimen reached until that level no longer can be reached. So usually it's like, for example, a 20% drop. So we usually define that. Okay, here is some examples of results that are expected. These are the envelope force drifts. These are relative deformations per mechanisms, where we can assess joint distortion, nonlinear bending, elastic bending, shear distortions. As you can see, shear is a very tiny proportion about the overall deformation. Energy dissipation capacity, which pretty much is the area of one cycle, and also the equivalent damping. We can calculate ductility index, which is the relationship between maximum deformation and yielding deformation. We can assess stiffness degradation and damage evolution, okay, per drift. This is very important because we can see how the structure is actually behaving under the cyclic load. Well, after that, we can actually check seismic vulnerability. Okay, we can create a scale per drift and damage index, where we can see a slightly damage would be just being cracked, or light damage would be joint cracking, and then moderate damage would be cover and spalling, and extensive cracking would be bar buckling, and then partial collapse, which would be the ultimate collapse. So what have we found so far about columns? So this is a summary of like a 50-page long state of the art, but I'll try to make it simple. So columns made of these irregular seismic principles, we can say that pretty much the presence of plane bars and lap splices, they reduce flexural capacity, lateral strength, increases deformability, decreases energy dissipation capacity, promotes wider and less spaced cracks, reduces ductility, increased reduction in initial stiffness. Okay. While also insufficient transverse reinforcement, they reduce lateral strength due to premature loss of concrete cover, okay, provoked by rebar buckling. Reduces confinement actions because due to decreasing ductility. We also checked that if we increase actual load on these columns, we actually might get a pseudo ductility. This is because of Brocking mechanism, which pretty much, if you enhance the loading on the column, you will have a flexural behavior mode type of failure. So this actually gives you a little bit of more ductility. And also, bidirectional loading can affect more capacity flexure than regular bidirectional loading. Okay, unidirectional loading. Sorry, and these are what we expect in the lab when we assess these types of elements. So very spaced, wide cracks, bar buckling, okay, and concrete spall out. Also related to beam column joints, this is what this is actually our major concern. But these elements are very sensitive to shear strains, okay, especially when they are unreinforced. In other words, they don't have like stirrups inside of it. They're very susceptible to shear brittle failure, especially when we have a combination of both directions of loading, which you can decrease confinement. And then by decreasing confinement, you lose bond strength. And especially when you have lack of stirrups in the corner joints, and especially when you have plane bars, you can have a premature shear failure because, well, the shred compression action is the only thing that upholds, promotes strength in the core joint. Okay. And since this scenario can happen, We have a type of failure that we call the concrete wedge mechanism, which actually the compressive strut just pushes the hooks outside the joint, and that can create a severe type of damage, and that can promote premature failure of the joint. Again, as I told you guys before, if we have a premature failure of these guys, doesn't matter if your building was capacity designed, it will fail by failure, shear failure. Okay. So what have we learned about beam column joints? So the external joints usually are more damaged than internal joints. The presence of plain bores and lap splices, they do the same thing as columns. They reduce flexure capacity, volumetric strength, increase the vulnerability, decrease anticipation, promotes wider and less space cranks, increases reduction in shear stiffness. Also increases slip in beam anchorage, which reduces flexure capacity and also increases fixed end rotations. Okay. So insufficient and lack of transversal reinforcement enable shear brittle failure, and adjacent members cannot reach their full capacity. Also, insufficient rebar anchorage can promote a sudden failure by pullout due to reversal loadings. So there is a certain disagreement among researchers about adjacent members. So like beams, transversal beams, what we call spandrel beams, and slabs. So some authors, most of them actually, they say that these adjacent members, they can actually increase strength because due to confinement. However, some other authors, they were not really sure about this, so a little evidence have they found about this. So there's not a very unique um, thought about this subject, I think, because most experiments are run through 2D experiments, and they are all based on pseudo-static loading, so which is not really related to earthquake loading. And I think if we'd have 3D experimental campaigns or shaking tables, would have better results about this. Also, beam column joints made with plain bars and no transverse reinforcement. As I said before, they disable adjacent members for reaching their full capacity by what we call a shear hinge mechanism. So like in this picture here, we have a 2D frame structure. And as you can see, the first floor is usually more subject to damage. And before the plastic hinge can be reached in the elements, such as columns, because this was like a weak column, strong beam type of structure, we had seen that type of shear hinge or shear failure, sudden shear failure being developed earlier in earlier states. Okay. So beam column joints are very delicate to elements to make interventions. This is something very, very difficult. So if we want to do retrofit, how can we do it in a surrounding joint? You know, so this can be very labor intense, and there is needs to reassess structure. So what do we mean about that, Jerry? So we have pretty much 2 types of retrofitting techniques. We have a local and global retrofitting. Global retrofitting is when you increase the overall frame by adding external members. And local retrofitting is when you want to recover or enhance a specific member capacity. Okay. And some of these interventions, they have to be really careful when we're doing with seismic performance. Why? Some of these retrofitting, they can alter the dynamic response of the frame. So if we increase exaggeratedly the section's capacity, we will increase stiffness, and we also will increase building mass. In other words, we're going to change the loading demands. Okay. Also, these local retrofits, they can also shift plastic hinge formations to under desired members. So for example, I can enhance, for example, beams, and we are supposed to have beams fail under seismic loading instead of columns. So sometimes we can enhance beams, and then we can decrease the forces that are acting on the beams, and they go to columns. So they can decrease the performance of columns. So we have to be careful about this. which can enable like sudden failure and facilitate premature failure. Okay, so reassessing the retrofit is actually something very important. Okay. Other techniques, talking about global retrofit, we can add shear walls or bracing and um, mass dampers, base isolations, wing walls. All these additions, they can either make the building have more strength towards lateral loading or decrease the seismic bend of the building. Okay, these are global retrofit examples. In local retrofit examples, we talk about retrofitting local members. We don't add new ones. Okay, so whenever we do that, we change the dynamic response of these local members. Okay, and most examples are jacketing. We can do like FRP jacketing, reinforced concrete jacketing, steel jacketing. We can enhance the size of the members. We can inject epoxy repairs. We can do removal and replacement. So we have many techniques that we can do this. And something that we are actually concerned about is the innovative seismic strengthening strategies. We want to use different materials and different techniques to increase performance, reduce costs, reduce labor, and some of the example of these are CFRPs and GFRPs. HPFRP, which is high performance fiber reinforced concrete, or the use of post-tensioning hardened systems, and the use of high-strain hardened cement-based composites. We are actually focused on CFRPs these days. We are going to run some experiments with it, and hopefully we can talk about this next. So the methodology of this research pretty much is the characterization of seismic behavior. As you can see, we made the state of art about this. So we know a little bit of what are the parameters that affect all buildings. We also want to validate equations in the new proposal of Eurocode 8. And to do that, we have to study the implementation of this retrofitting and calibrate numerical examples based on experiments. So these are the next things that we are actually going to come up with. We are going to run an experimental and numerical campaign. We would like to build 4 frames, 4 beam column joints, and 12 reinforced concrete structures made with not made for seismic loading. We want to, for the frames, test in shaking tables, and for the other elements, we want to do cyclic tests in order to collect data. And then we want to, some of these elements, we want to test these strengthening techniques. And then finally, after experiments, we are going to check that analytically. Okay. So these are some of my references. I didn't put all of them because there were over 90. And well, thank you so much for your attention. If you guys have any questions, just let me know. Okay.